This lesson will focus on the interference of waves and the superposition principle. Alright, so up to this point we've looked at what happens when a wave interacts with a boundary, that is a fixed end or a free end. And we noticed that, again, think a wave is energy. When a wave interacts with a boundary, that some of the energy is reflected off that boundary and some of it is transmitted into the new medium. Okay? Well, what happens when two waves interact with each other? Now think of this and kind of relate this to matter. Okay, if you have two pieces of matter, can two pieces of matter occupy the same space at the same time? That's saying, if let's say I have, I don't know, person 1 and person 2. Okay, say they were going to meet at spot X. Okay, can these two people both be at that same spot X, the exact point at X, at the same point in time? Okay, and the answer should obviously be no. If these two individuals walk towards each other, walk towards spot X, when they meet at that point, what's going to happen is they are going to collide. It's not physically possible for matter, like us or anything, to occupy the same space at the same time. Now, in class you should have done some investigations on what happens in a snaky spring on a simulation. What happens when two waves meet? Do they bounce off each other like matter does? Okay. Well, the answer there was no. So this whole really deals with what property called interference. When two waves meet, you should have seen that they combine to form a larger wave. Now, I'll be careful with saying larger. Sometimes they would form a smaller wave. Right? Then after basically forming that larger wave, they return to their normal shape and then move in their original direction. So basically the two waves are going to pass through each other as if nothing happened. Okay, this process in which the waves pass through each other to form a larger resulting wave is known as interference. Okay, and interference is a principle that's seen in both sound waves, ooh, there's my arrow, sound waves, mechanical waves, as well as light waves. Okay, so interference is a property that's basically specific of all waves. And interference is the main difference between matter and waves. Matter cannot interfere with each other. Waves can. Okay? Interference, again, is basically adding and resulting in a larger wave. Matter cannot do that. Waves can. This is the primary, distinct property that separates waves and matter. Alright, so when looking at the waves, when they interfere with each other, what property changed? Well, you should have noticed that the one property that changed was the amplitude. When two waves interfere, since they're in the same medium, okay, the speed is the same. The wavelength, therefore, it would depend really on the wave, but the wavelength was not affected. The frequency is not affected, but the one property that is affected is the amplitude. Why do you think that is? Okay, well, what does the amplitude represent? Remember, there's a relationship between amplitude and the energy, where energy was associated with the amplitude squared. So the amplitude simply represents the amount of energy. So when two waves interfere, what's happening is the amount of energy that's at that specific point in time increases. Alright, now this gets a little tricky when we talk more about the types of interference and destructive interference, but as of now, just think about it, the amount of energy at that one point is greater. Okay, and that's shown by the amplitude. Alright, so when two waves meet, the main thing, the principle which they follow is called the superposition principle. Now this is a principle that, yes, relates to interference of waves, but this is a simple principle that relates to many things in physics. Okay, superposition is a fancy term that represents addition. Okay, so it's basically the addition of two waves. So like I said, superposition is the algebraic sum. It's basically a fancy way of saying it. So when two waves meet, the amplitude of the resulting wave, that's the wave formed by the two waves, is the algebraic sum of the amplitudes of the initial waves. So the amplitudes of both waves that are interfering with each other will add up, and they'll either add up to form a larger wave, or they'll add together, they form a smaller wave. Okay, so we're basically going to be adding amplitudes here. Okay, the key thing to understand is we're going to look a lot at crests and troughs. Transverse waves. And remember that a crest and a trough are the properties of that wave, the characteristics of that wave. So a crest we see as a positive amplitude, and the trough we see as a negative amplitude. Now this is where it gets tricky when you think of amplitude and energy. You know, if you have a negative amplitude, wouldn't that associate with negative energy? Well, energy cannot be negative, but I guess in this case we're going to look at it as a negative amplitude, negative energy. Okay, but still be careful with that. Remember, energy cannot really be negative. All right, another way to think about this, or another term that we introduced with boundaries, was the phase of a wave. Okay, when two waves meet, it really how they interfere, whether they add to form a larger wave or a smaller wave, depends on their phase. Okay, so remember the phase is represented by a crest or a trough. It could also be a compression or a rarefaction for a sound wave or a longitudinal wave. Okay, so when two waves meet, they can either be in phase or out of phase. This is something I defined before. And in phase means that you have a crest meeting with a crest, or I guess more specifically, a positive amplitude meeting with a positive amplitude. Doesn't necessarily have to be the maximum peak of that crest. You could have a peak interfering with a part of a crest. And then out of phase would be opposite phases. So you have a crest, which is represented by a positive amplitude, meeting with a negative amplitude. Okay, so I'll kind of show you some examples of in phase and out of phase. But with in phase, you get an addition or a larger wave. Out of phase, you get a smaller resulting wave. So here's kind of a picture that shows in phase versus out of phase. Notice on the top diagram I have two waves, one traveling to the right, one traveling to the left. Notice they are both crests. Okay, so when they interfere, they would be interfering in phase. And then kind of taking that diagram, flipping it upside down, you could also have a negative amplitude meeting with a negative amplitude. They're the same phase. They're also going to interfere constructively or make a larger wave. And then out of phase is the opposite, right? You have a crest meeting with a trough, or a trough meeting with a crest. Okay, and those will form a kind of a cancellation of the waves. All right, so the interference depends on, obviously, like I said, the phase. So two waves will either form a larger or a smaller resulting wave. We really break this down into two different types. The first type is constructive interference. Okay, this is when two waves of the same phase meet, and what's going to happen is they're going to combine to form a larger wave. Okay, I'll draw this here in red, a larger wave. Okay, so they're going to constructively interfere. Destructive interference, on the other hand, deals with two waves of different phase. They're out of phase, combined to form a smaller wave. So here you would have a crest meeting with a trough. And what's going to happen is you're going to get some cancellation of the wave. This cancellation can result in a smaller wave. In this case, maybe, let's say the crest is larger, you can get a smaller wave. It could also result in the total cancellation of the wave. Okay, so you have a larger wave here, smaller wave there. Constructive versus destructive interference. All right, so here's kind of a diagram showing what's going on. Constructive interference, what you have, a crest meeting up with a crest. Notice when they are at, because they are waves, they're at the same position in time, shown here. Notice that you have the red wave has an amplitude of 1 unit there. The blue wave has an amplitude of 1 unit. Notice the resulting wave is a combination of those two. So it has a resulting amplitude of 2 units. So you're simply adding it, right? Same thing if you had two troughs meeting together. Meeting together, they both have an amplitude of 1 unit, minus 1 unit in this case. So their resulting amplitudes would mean minus 2 units. So just simply adding them together. Okay, not that difficult. Destructive interference, like I said, is kind of the opposite. Here you have opposite phase interacting, so you have a crest meeting with a trough. But what happens when those two meet? Yes, they're adding together to form a resulting wave, but notice here, the crest and the trough, you have positive 1 unit, negative 1 unit. That's going to result in 0 units of amplitude. Okay. Same here, you have 1 unit there, negative 2. When they meet together and interfere, you get negative 1. Results in a smaller wave, a cancellation. Alright. Notice with this interference, the one thing with matter, right, again, they would collide and rebound. With matter, they can't be in the same point at the same time. So what's going to happen is that they are going to just collide and bounce back in opposite directions. Same with when a wave hits a boundary, some of that energy is rebounded back into the medium. It goes in the opposite direction. And then remember, the phase depends on the type of boundary we are facing. With interference, however, the waves are going to travel through. When they meet at this point, they're going to interfere, whether constructively or destructively, following the superposition principle, and then they're going to pass by, continue on in the same direction at the same speed. Interference, key thing here is it does not affect speed, okay? Because that wave is staying within the same medium, and the speed of the wave depends on the medium. So interference does not affect the speed of the wave, where it would affect matter, where matter would collide, like in collisions, bounce off. You could have elastic or inelastic, right? In this, they're passing by, they're not affected. So it's like two lonely ships passing by in the night, as if they weren't even. All right, now a special case of this type of interference, total destructive interference. This is kind of a special case. Now, not all destructive interference is going to be total destructive interference. Alright, so destructive interference is when you have two waves with the same amplitude and the same wavelengths. Okay, so they're perfectly lined up. They're perfectly out of phase. Okay, perfectly out of phase. Meaning the resulting wave, you have positive one, negative one. The resulting wave is going to form with an amplitude of 0. So the waves completely cancel each other out. And this is an important aspect that we're going to cover in both sound, which we're going to do in this unit, and it also affects light. Okay, so total destructive interference is a special case of destructive interference, but it's very important to physics. Key things there is that the amplitudes are the same and also the wavelengths, and they're perfectly out of phase. Okay, so kind of how to do this interference, pretty simple, like we said. It's the superposition principle, simply adding. So, given a problem with interference, the first thing you need to do is just determine the phase of the wave. Okay, is it a crest or is it a trough? Then determine the value of the amplitude. Okay, does it have a positive amplitude, negative? That's, again, the phase. And what is the value of that amplitude? Then at every point in time, add the amplitudes together, and that basically sum will give you the amplitude of the resulting wave. Alright? And again, remember that time is that one variable that's always constant, it's always independent. Right? So that will be the one variable that doesn't change. Alright, now interference hopefully should be easy. Now with interference, we're going to come back to this when we talk about sound. Okay, right now we're mainly looking at just mechanical waves, transverse waves. We're really hammering down the properties of waves, the simple properties. But we're going to get to sound waves, we're going to get to light, and we're going to get to interference of both of those things. Remember, interference is the telling sign for waves. So if two things interfere with each other, meaning they pass through, they add following the superposition principle, that is the one single sign for waves. If they don't, then it's matter. Okay? So, you could have sound waves that interfere with each other. Okay, if you think of where this is seen, what is an example of where sound waves interfere? Well, there is, I think I'm spelling this wrong, probably, but acoustics. That is completely wrong, right, on spelling. But, let me erase that because it's disgusting. But acoustics, right? Think of like an auditorium or something like that, is that they basically create an auditorium or that theater type seating such that the sound waves basically will constructively interfere. You'll get places where the volume will be nice. That's why you can sit far away in an auditorium but still hear the actors on the stage as if they're right in front of you. There's also some places in a amphitheater or whatever where the sound waves will totally cancel each other out. You may have heard the term before, dead spots, right? Those are locations in which the sound waves totally destructive interfere with each other and cancel each other out. So sound is a wave, can interfere in such a way that it cancels out. Light is also a wave. Light can also do the same thing. You can have light waves that interfere with each other and add up to form a more intense light also can cancel each other out to form basically no light, okay, or a smaller amplitude. Now the funny thing is, we talked, yes, matter is different than waves in that it can interfere, but matter actually can also interfere with itself. There's kind of the wave-particle duality. You may have heard of this before, and we'll talk more about this as we get later in the semester, but matter also inhibits both wave and particle-like nature, meaning that they'll show sometimes that they can collide, and they'll sometimes show that they can interfere with each other. Okay, so that interference shows that it has some sort of wave-like nature. Now we'll come back to this. If you'd like to look at a video of this in more detail, follow the link below here. Kind of goes through something we may have watched last year called Dr. Quantum, where he kind of briefly explains what happens with particles or matter and wave and how they exhibit this wave-particle duality. Okay, but that's kind of the main things with interference. We're going to come back to interference, especially this unit with sound waves. Okay, so kind of take some of the main things out of here, and that the amplitude changes as well as the wavelength is also what affects the phase. Okay, some of those things are going to affect how sound waves also interfere. Okay, and then on the last, so this slide here, if you'd like to see more kind of an animation on how constructive interference looks, follow this link. If you want to see how destructive interference looks, follow this link. Okay, it's just kind of an animation to show you how they add up following the superposition principle to result in a smaller wave.